My name is Keith Kinch, Global Head of Marketing for Gradiant, and I'm joined by my colleague Anish Kumar Selvan, Gradiant's Global Product Manager for Cure Chemicals. Anish has held diverse and progressive roles at Gradiant, spanning R&D, process applications, marketing, sales, operations strategy, and customer excellence. He currently leads Cure Chemical product management globally, ensuring robust infrastructures in Malaysia, Italy, Saudi Arabia, and India. We're thrilled to have you today as we highlight some advancements in the field of water treatment and sustainability, particularly on membrane systems and membrane performance, specifically how we can maximize performance through innovative chemical solutions. And what we'll go through here today, we'll give you a little bit of a background on membrane systems and operations, as well as some of the innovative solutions that Gradiant has brought to market that help our customers protect their assets, maximize uptime reliability, and ultimately save you money. So first, let's go over some housekeeping for today's webinar. If you could go to the next slide. So today's webinar, we've got 60 minutes, including a Q&A session at the end. This session will be recorded, so replays are available. So if you have some friends or colleagues who want to watch the webinar, they'll be able to do so offline. They just have to register. We do have participants in listen-only mode, and that will make sure that our speakers can present without interruption. And then please do submit questions at any time. You see the little icon there on the slide with the yellow box around it. That's how you can submit a question. What we have found in these webinars is we get more questions than time to answer. So we'll try to get to as many as we can, and then those that we cannot, we will follow up with folks after the webinar. All right, next slide, please. So a little bit about Gradiant first. For those who may not be familiar, I can go through a little bit about our company and our history. We aspire to be a different kind of water company, and really it's what the thread you'll see throughout the history of our company is that we bring together a very innovative and proprietary technology stack that ensures that we can solve any number of water challenges. And those solutions go beyond just equipment technologies. In recent years, Cure Chemicals is one of the examples of a chemical product line and services, as well as AI, Smart Ops AI, to help companies run their systems more sustainably and effectively. Next slide, please. All right, and what drives Gradiant? This really is the backbone of our company and what drives us. So first, around our vision, this really is about elevating water, and we really want to redefine how the world views and utilizes water, turning it from more of a limited resource into a highly valued asset. And we do so through innovative technologies and visionary leadership. That way we can elevate water to its rightful place as the foundation of a sustainable future. In terms of our mission in giving nature water back, this really is about restoring the balance to the planet's water cycle by delivering water solutions that treat, recover, and reuse water with precision and care. By giving nature water back, we do ensure that our essential industries can thrive responsibly while still protecting ecosystems that do sustain the planet. And then lastly, the purpose, ensuring water for generations to come. At Gradiant, our purpose really drives our passion to safeguard the world's most vital resource of water. And we do so by creating solutions that support water availability for future generations. And this, in turn, can help ensure a water-secure future for both communities and industries alike. Next slide, please. So without going into detail of all the different years, we are a company that's now been around for not quite, but almost 12 years, founded by our two founders who met and commercialized their technology out of MIT and spent the next handful of years commercializing that technology. And then had the foresight in 2018 to open up an innovation center in Singapore that really was the catalyst to the growth that we've been experiencing over the last handful of years. There we developed some other unique and innovative technologies like CFRO technology for MLD and ZLD applications. We've then acquired some companies all over the world that expanded both our product portfolio as well as our geographic presence. And then this past year really was a very exciting year for Gradient in launching some very new and innovative technologies, including Forever Gone for PFAS treatment, Alkali for lithium recovery and battery mineral recovery, as well as Cure Chemicals. So these are all some very landmark innovations that we launched through the year, and is one of the reasons why we're now looking to talk to more folks in industry about some of the applications we've got expertise in the Cure Chemicals field. So next slide, please. And really, as I mentioned, the desire to reach more customers, to help our international and multinational customers, we have grown from having a global headquarters in Boston to establishing a regional headquarters and global innovation center in Singapore, and then more recently last year establishing another regional headquarters and global innovation center in Abu Dhabi. So this investment in technology advancement, in being where we see some of the biggest challenges in the water industry appearing, are driving some of those investments. So now, we're operating with with 20 global offices now across 90 different countries where our customers are located. So really, it's about getting to those customers, those sites globally with a local focus, and also even a global set of experts to tap into. Next slide, please. And to give you a little sense of our technology portfolio, across the top, this is primarily a lot of the unique and proprietary technologies that Gradient employs across a number of different water applications. But you can also see, some of these aren't necessarily proprietary, but what is unique is both the combination of some innovative technologies that Gradient has developed, but also the ability to engineer customized bespoke solutions for clients, because every situation at different sites is quite unique. So having that flexibility to be able to deploy both proprietary technology, but also other technologies from other companies allows us to design solutions that ultimately save capital, save operating costs, and minimize those operational risks. Next slide, please. And as I mentioned before, we do serve the world's essential industries. So everything from food and beverage manufacturing to semiconductor manufacturing, which has been quite expansive over the globe over the last couple of years, and certainly into the near future. But then also pharmaceuticals, renewable energy, oil and gas, chemicals industry, automotive. So where those customers have unique challenges, particularly around making water fit for purpose for use internally in the plant, but also ensuring that they're able to meet compliance on discharge, and even more so, start to save more water and recycle that. And over the course of our history, the vast majority, even 70% of our customers are from that Fortune 100. So those exacting standards that our clients expect are really what drive the innovation that we bring to the market. Next slide, please. Okay, so before we get started, we wanted to ask a couple of questions from the audience here to get a little bit more information on who's on the call today. So we'll go ahead and ask these poll questions. All right, so first is what industry are you in? Just please select one, share your results. We'll give folks a minute here or a few moments to just answer the question before we move on. All right, we're almost up to a half. See if we can get a few more folks to answer the question. right, almost there. All right, looks good. We've got a good percentage of the audience, so it looks like we've got looks like between refining chemicals, power energy, those seem to be higher. Oh, and then general manufacturing at 30%, refining chemicals at 26%, power energy 19%, commercial institution 19%, food and beverage 7%. Okay, so a good mix, a good mix. So that'll make for an interesting dialogue here today. All right, I think we have one more question we wanted to ask, and that's really, what is your role within the organization? So that might help us tailor a little bit of what we talk about today to meet our audience's needs. All right, looks like give a little bit more time here. It's looking like a little more than a half of the audience is in process and application engineering roles. 18%, we've got some R&D or water doctors, and then some smaller percentages here for procurement, operations, and management. Okay, that should be good for the poll today. Okay. All right. Well, now that we've gotten a little bit of some information on the audience here, without further ado, let's dive in and explore how Gradient's Cure Chemical Solutions can improve operational effectiveness and cost. All right, take it away, Anish.
Thanks, Keith. Hey, good morning, everyone. Thanks for being here. Firstly, it's exciting to see a wide range of attendees joining this webinar across different industrial verticals. So, as Keith mentioned, it'll be an interesting dialogue, especially in the Q&A part. So before we get into the subject of today as membrane chemistries, which is one part of a bigger portfolio, which is cure chemicals. So these are specialty chemicals for water and process treatment that Gradient services into the global markets that Keith talked about, 90 different countries under Cure brand name. So what does Cure mean? It means chemistries for utilities, recycling, and equipment. So Cure has over 400 specialty chemicals across water value chain, primarily for 6 treatment applications, starting from cooling tower and boiler system in a typical industry. It's called utilities. We have utility chemical treatment, we have membrane systems, we have wastewater treatment chemicals, water clarification, and process treatment. These are process chemicals that goes into different industrial verticals again. So these are the industries which currently uses Cure chemicals both on the process side but also on the water treatment side, starting from oil and gas and petrochemical refining, food and beverage, mining, metal, paper and pulp, so on and so forth. Leveraging our strong gradients application expertise with specialty chemicals along with the digital solution offerings put together to optimize the performance of your operation. So what does the Cure product range look like? These 400 chemicals spanning across these 8 product classifications broadly, starting from corrosion inhibitors and scale inhibitors to safeguard your critical equipments where the heat and mass transfer happens in systems like heat exchangers, boiler piping, cooling systems, etc., etc. And we have process chemicals additives. These are specialty chemicals for tailoredly made for specific industries like mining, petrochemical refining, pulp and paper, and many more. So we also have defoamers and antifoams to prevent and eliminate foaming from the treatment processes. And we have antiscalant and cleaners. These are very specific for membrane applications to inhibit scaling and fouling within a membrane. We have biocides, both organic and both oxidizing and non-oxidizing biocides. We have antifoulants to inhibit fouling in a treatment process. And we have the polymers of coagulants and flocculants in the primary treatment of water clarification. So today we will specifically deep dive into the membrane chemistries. Before we get in there, I'd like to outline the webinar objectives for today. First is to understand the key challenge impacting membrane performance. Second, to get into the science of why it happens, how it works. To get into the science of these membrane challenges commonly as scaling, fouling, and membrane degradation. So we understand the science and then we tackle with our solution. So understanding how QR chemicals look at these specific operational challenges and then we provide our solutions to enhance membrane efficiency, longevity, and sustainability being the key driver in selecting a chemical program and share our success story and of course cure differentiators. How are these cure chemicals different from the providers in the market today? So assuming some of us in this webinar are new to the membrane technology, so let me start by saying membrane is one of the most impactful innovations in the water treatment industry. Primarily, I say because of three reasons. One, because of its disruptive efficiency. Membrane systems transforms the water treatment with its high recovery, reliability, high quality of water production at a much lower cost of operation when we consider the huge volume. For example, in a typical desalination, without membrane solutions, this wouldn't have been possible what we have today. So membrane systems does handle a huge volume, producing a very high quality at low cost of operations. And of course, it is very sustainable because it uses relatively less energy and produces less waste, promoting greener water management. So to understand this better, membrane is basically a semi-permeable filter. So what it means is it allows certain things to pass through while leaving the salts behind. So a salt solution, when we pass through a filter, the salts are deposited in the membrane while the water part alone pass through the membrane. And we have several membranes in the market for different functions, starting from microfiltration, ultrafiltration, nanofiltration, and reverse osmosis membranes. So on the principle part, we can better understand this by knowing the principle of how an osmosis work. So if you take this, let me put my laser. So if you take this image, if you have a salt solution that passes through a membrane, what naturally happens is the solute on the region of a these circles that you see are salts, otherwise called solute, and the water part is called solvent. So naturally what happens is the solvent that has low solute concentration tries to move towards the region of a higher salt concentration. That is natural osmosis and the pressure the solvent exerts is osmotic pressure. So how reverse osmosis work is by reversing this natural cycle by exerting an additional pressure to squeeze the water component out. Hi. Good. So the reverse osmosis works by applying the additional pressure by squeezing the solvent through the semi-permeable membrane, leaving the solute behind and only get the solvent out of it. So any typical membrane operation has three components, starting with the pre-treatment, which is foundational and fundamental in a membrane operation. So any water, whether you get it from industry or surface water, it has to be conditioned and then take it to the membrane system because these water have suspended solids, turbidity in the water, organic content, which are enemies of a membrane. So we have to take it stepwise, remove those TSS, turbidity, organic content in the pre-treatment site, and then take it to the membrane for the dissolved solids removal. So whatever drinking water that we have today, everything has gone through the membrane and the dissolved solids in that water is removed by the membrane technology. And the post treatment, whatever water comes out as treated water from a membrane has to be conditioned again, either by pH correction or remineralized to improve the conductivity required for the point of use. So commonly, membrane has four contaminants or impurities, which are classified in this table below. First is ionic or inorganic content, which are primarily the cations and anions in the water. These are calcium, magnesium, chloride, nitrate, sulfate, carbonate. So these are the cations, anions fall into the inorganic first category. The second category being organics like alcohol, ketone, phenols, aldehydes. And the third categories are particulate matter. These are suspended solids, colloidal material, and these microbiologicals like bacteria, virus, algae, so on. And last but not the least, the gases which are in the membrane, because when the water absorbs air, it has dissolved oxygens, carbon dioxides, chlorine, nitrogen, so on and so forth. So these are the key aspects or the impurities of a typical membrane. So membranes bottoms up. Understanding membranes a little more from a microscopic level to a system configuration. Any typical RO membrane is made of three layers. The first and the bottom layer is polyester fabric. This is a strong support base. The middle layer is a microporous polysulfone base. So this is the cushion. This is the extra support for the yellow layer here that you see are made up of polyamide barrier layer. So our outer membrane is this yellow layer being supported by these two polysulfone and polyester fabric layer. So, and then this is a flat sheet membrane. Any membrane that you see in a coil form, the raw material is a flat sheet. And then you put a feed spacer in the middle to create turbulence, to allow the water to flow through each flat sheet membranes. And then you pack that with a permeate spacer. When you do that stacking to the required length, and then you coil the membrane. So this is spiral wounding process. So a water that comes at the feed side travels spirally through this membrane, and whatever the deposits, whatever the solids that these water have are being catched by these membranes, and then the clean water comes out as permeate from the middle perforated tube. So the middle one is the permeate, and the brine is rejected separately, or the reject water is taken out in a different port that you see here. So each element put together in a pressure vessel becomes a membrane vessel. Uh, so this pressure vessel schematic has three membrane elements. It has a feed port where we pre-treat the water, take that water into the membrane system, and we have a permeate port. The perforated tube in the middle produces the treated water, and we collect the concentrate here. So this is just one pressure vessel. How does a system look like? So what we saw here, what we all saw here is going into these pressure vessels of an RO system. So here is a typical example of an RO system that has three stages. So we use multi-stage for higher recovery, and we use multi-pass for higher purity of water. So in this example, we have about 50 million liter, 58 or so coming at the feed water side. Stage 1 is 65% recovery, which means 65% of the treated water at good quality comes at the permeate side, and then the reject goes as the feed for the next stage, and this reject goes as the feed for the third stage. So you basically enhance the water recovery by adding more stages. So put together, we have about 75-80% of water, fresh water being recovered from the feed water. So what are the key challenges impacting a membrane performance? So our first objective is understanding what are the challenges. First being scaling. So what does scaling mean? It is precipitation and deposition of sparingly soluble salts. So what does sparingly soluble salts mean? So these are salts which dissolve very little in the water. So when they are in the ion form, and when the cation and anion join together becomes a salt, these salts becomes difficult to dissolve in a water. So this is scaling, and the ideal conditions for scaling are when the concentration of a salt goes higher than its solubility limit. So solubility limit is the limit before which it will be in the dissolved phase, after which it will become precipitate and become salt and become solid crystals, so on and so forth. So higher concentration of salts and excessive recovery rates are the key reasons for scaling to occur. And then the alkaline pH levels promote the scaling to occur. To give you an example, calcium carbonate is one of the common salts that everyone faces. So carbonate becomes more stable and stronger at a higher pH level. Here it's between 9 to 10, it becomes more stronger and it will precipitate out as calcium carbonate salt. I have given some listings of the common scaling salts in a typical membrane operation. So scaling being the first key challenge, then comes the fouling. What does fouling mean? These are accumulation of organics, colloids and biofilms which clogs the membrane surface or pores. So when microbes they grow together, they form a shield. It's called biofilm. When that biofilm clogs the membrane pores, it doesn't allow the water to pass through. So this is a performance reduction. Likewise for the scaling, these are inorganic salts which clogs the membrane surface. Fouling is organic matter that clogs the membrane pores. So the ideal condition for the fouling to occur is when the pre-treatment is not done properly to remove the organics upfront. So if the organic loading, because of high COD, which is chemical oxygen demand, high ammonia, high phosphate, there is the natural tendency of fouling to occur. If the TSS and turbidity is not removed upfront with the pre-treatment site, then those are going to be accumulated within the membrane, and it's very difficult to clean them. So the key reason is inadequate pre-treatment. And these are the two metrics of fouling control. One is slit density index. So the membrane manufacturers largely recommend to have this within 3. So SDI means it measures the fouling potential due to the suspended solids in the water. So recommendation is to keep within 3, lower the better. The second metric is turbidity, to maintain within 1 for the warranty of the membrane for its designed service life, and for the peak performance to keep it below zero point 0.2 for high recovery applications and so on and so forth. So scaling, fouling, and the third challenge for the membrane is membrane degradation. So this is a permanent damage to a membrane causes because of a physical or a chemical or an oxidative damage to a membrane over time. So this don't happen rapidly. This happens over time. So how it happens? Largely through oxidation effect. When during cleaning cycles we use dechlorination agents, so there is a chance for leftover free chlorine in the membrane systems. If chlorine is an oxidizing agent, so chemicals exposure to oxidizers, sorry, membrane exposure to oxidizers like chlorine and metal presence. So the metals are catalysts for chlorine. So chlorine being an oxidizing agent, it will oxidize the membrane surface, leading to the 3 effects. First is the structural degradation. So these polyamide membrane surfaces becomes damaged, and second is loss of selectivity. So a membrane is designed to block salts and allow water to pass through. It will lose its selectivity design. The third is increased permeability. Because of this oxidation, the hole size becomes bigger. It allows the water along with the salts to pass through, which is a permanent damage of a membrane, irreversible sometimes. The second condition for such thing is extreme exposure to pH and temperature, so leading to polymer degradation that we just saw. The third is mechanical wear. High pressure fluctuations at the feed water side will eventually create the shear effect and erode the membranes. With that, we have a second poll session here to understand your drivers for selecting a chemical program. Over to you, Keith.
All right. As Anish said, we've got our next poll question coming up here, being what is the biggest factor in selecting a membrane chemical program? And this is really for you and your site or your range of sites. This again is just helps us understand more of the drivers. Certainly we can design programs to solve any or all of these challenges, but we like to get a sense for is it product quality driven? Is it more cost driven? Is it the after sales service that comes along with a chemical program, or even just the nature of the chemistry itself. So we'll give folks a minute or two to answer the question. This helps us again with tailoring some of our discussion today, but also in product development helps us with that as well. Seems like we're getting a little over half now. Seems like the performance consistency at 44% and cost effectiveness at 32% are the bigger proportions here. So why don't we go ahead and end that poll? Thank you for voting. And then the next question is, what is your primary water treatment challenge? Is it scaling and fouling prevention? Is it to lower your operational cost? Is it membrane longevity and maintenance? Or is it to optimize your process? So we'll give folks another minute here to answer this question. Okay, getting a little more evenness across all the different areas. Pretty well distributed, it seems. We'll give folks another moment here. We see the voting start to slow down. We'll close the poll, but looks like here pretty even, 36% scaling fouling protection, 28% membrane longevity, 24% process optimization, 12% lowering operational costs. So it seems we've got about almost 60% of the vote here. So we'll go ahead and close that poll and hand it back to you.
Thanks, Keith, and thanks for all your polling. So earlier we talked about the challenges, the key challenge being scaling, fouling, and membrane degradation. So how do we tackle that one at a time? So for scaling, we use antiscalants to inhibit the crystal formation and the further growth of that crystal. Second, the earlier we saw excessive recovery rates being an ideal condition for scaling. So we optimize that recovery to minimize polarization effect. So this is a technical term which means solute buildup at the membrane site, creating a concentration gradient that eventually damage the or reduces the membrane performance. And of course, the right pre-treatment is ideal to avoid scaling within the membrane. For fouling, we use filters like multimedia filter, cartridge filter. We do primary clarifications like coagulation, flocculation, sedimentation to remove all the suspended solids and turbidity that could potentially or possibly enter into a membrane operation. So we filter that at the pre-treatment site, and then we do biocide dosing for the membranes for the control of fouling and biofilm formation. And of course, we regularly monitor the key parameters like pressure, pressure drop, and permeate flow, etc., to ensure we are well within the fouling control. And the third, membrane degradation, we use dechlorination agents to kill all those free chlorines that could potentially oxidize a membrane. So we have dechlorination agents that are dosed appropriately at the right dosage and time to avoid any physical permanent membrane damages. And of course, to operate the membrane system with the right recommended guideline, to follow the right pressure, to have the right pH. A pressure for the brackish water could be 10 to 25 bar. For the seawater could be 55 to 70 bar. And pH, of course, between 6 to 8, but ideally at a neutral pH of 7. And temperature definitely have to be below 45, ideally below 40 degrees centigrade. And of course, conduct regular inspections fully supported by the Smart Ops digital solution offering combined with our chemical program that will eventually maximize the hour performance, optimize your water use and energy and chemical dosage, of course, minimizes the environmental impact, and of course, higher return on investment for our customers and stakeholders. So with that, this 2D schematic gives you a very good understanding of end-to-end membrane treatment from a chemical perspective. So we first have the water clarification. This is the pre-treatment chemical part, which I talked about. We have the suspended solid removal by adding coagulation and flocculations to remove that turbidity from the water. So these could be ferric chloride based coagulants. And then we have disinfection to remove any microbes present in the water that could eventually, if not addressed at the pre-treatment site, could damage the membrane here by forming biofilm or biofouling. And then we have dechlorination agents for the membrane degradation part. So we have several range of chemistries here. The ones listed are star multi-purpose product for different water chemistries and complexities. The next is scale prevention. These are antiscalants. We have a whole range of 40 plus antiscalants that we have commercialized that can work very well with your water. And of course, cleaning is paramount important for a membrane performance. So we have a lot of cleaners, acidic, alkali, silica, so on and so forth. And of course, the post-treatment remineralization to condition the water, maybe a pH or conductivity required for the point of use there. So we will go one at a time, starting with antiscalant. So antiscalants are chemicals which inhibit a scale or a salt to form and grow further. And these are the common salts which could potentially scale in a membrane system: calcium carbonate, calcium sulfate, calcium phosphate, barium sulfate, so on and so forth. The way it happens is this mechanism. If you see, when cations and anions combine, they become a salt, and these salts have a perfect structure that let salts to aggregate together. So first it forms, then it orders, and then it becomes a perfect cubicle, and this multiplies within a water system. If not an antiscalant is used, this is scaling in a membrane. So if you see, these are microscopic visions of a calcium carbonate salt, a calcium sulfate, which has a rod-like structure, a calcium phosphate like a needle structure. If you see here, the perfect cube can accommodate another cube, can accommodate another cube at all the dimensions. So so the way antiscalant works is with these three mechanisms which we deploy. First is threshold mechanism. So the antiscalant chemicals will prevent a crystal formation before its scaling threshold. So there is a technical term called solubility product. This talks about the precipitation behavior of a salt. So we know that number, beyond this number that will become salt, before this number that will be in the soluble form. So the antiscalant will ensure that the salts remain in the before uh, remain in the ionic form and not become a salt and agglomerate. Crystal distortion is a structural modification step. So these chemicals will modify these cubes into a sphere in calcium carbonate case. So the spheres, they don't easily combine together, unlike a cube. So it structurally modifies. And third is dispersion. Basically, this is an electrostatic repulsion effect. So these antiscalants will cover the salts with ions, and they tend to repel the one calcium carbonate cannot combine with the other because of the electrostatic repulsion, similar to a north and north of a magnetic pole. So the objective is with antiscalant, the membrane flux, the permeate flows maintained, and without antiscalant, of course, the membrane performance declines with time. So scaling is not just in membranes, it's membranes and other key applications where temperature is involved, like heat exchangers, boiler pipelines, which creates heavy performance hampering. So prevention is essential for a scaling treatment. Um, so this matrix gives a good understanding of the scaling salts with our antiscalant products. If you see some of our phosphate specific wastewater, very good works in the wastewater treatment, some sulfate, some are silica based, some are multi-purpose which can tackle all at the same time, and some for the desalination specific antiscalants. So the take back is we have a comprehensive range of antiscalants that can work wonders tackling these salts. So antiscalants are going on a paradigm shift. Today, it's all phosphorus based, which has phosphates, phosphonates, and chelating agents, which does its function to keep the antiscalant working. But these phosphorus are not environmental friendly. They create eutrophication. Basically, these are nutrient buildups that promote biofouling in a membrane system. So these chemicals are not environmental discharge friendly. So we are moving towards a phosphorus free formulation. The market is moving towards which are not phosphorus based, but we use synthetic polymers along with organic acids and biodegradable agent. But still, these doesn't fully solve the problem. So the next shift in the next 5 to 10 years we expect is completely bio-based polymers. So these are environmental friendly and completely eliminate the toxic or resource heavy elements part. So this is the paradigm shift that's going towards. And Gradient today has commercialized a lot of products in this phosphorus-free zone, and we are in the R&D of testing this bio-based polymer in this paradigm shift. And we continue to diligently do R&D to further improve our efficacy of all the current products and the new product development. So the second key issue is fouling and biofilm. So we have two product range, one being anti-foulant. So they focuses on particulates, colloids, excluding microorganic organisms which are tackled by biocides that you see here. So both of them produce fouling in a membrane. If a microbes produce fouling, these are biofoulings. If not, these are normal foulings that is in a membrane. So the way it works is these chemicals, they modify the surface and create an electrostatic repulsion to further aggregate. And of course, similar to antiscalant, antifoulant works. And biocide, because these kill the cell, these kill the microbes by first disrupting the cell wall, and these chemicals get into the cell wall and create a cell death to avoid any form of biofilm formation that is difficult to treat. If you see here, this is a clean membrane element and this is a biological fouling. So to reverse this from this to this is challenge. So we treat it with our biocides at a much earlier phase rather than letting it worse. So these are some of the biocides we have, oxidizing and non-oxidizing. Oxidizing kill the microbes, whereas non-oxidizing they just disrupt and inhibit without oxidation process. So these are some of the chlorine-based and DBNPA-based biocides we offer. So as I mentioned before, cleaning is a paramount important. But when do we clean an RO system? I'll wait for maybe a few seconds for you to think through. What are the leading indicators to clean a membrane? First is the pressure, and second being flow, the third being the quality of the permeate water. So if the pressure goes, so this is a typical RO skid. This is the feed header, permeate header, and the reject header. So when the pressure in the feed header goes above 15% than the design, it means the salt starts to build up. It indicates scaling effect. And the pressure at the permeate sides goes lower and the reject sides goes higher. Okay, it indicates scaling has happened. And of course, flow. So if the permeate flow goes lower than 15%, it indicates I have to start cleaning, kickstart the CIP process. So there's two cleaning methodology, the alkaline or high pH CIP for fouling control and the low pH CIP acidic cleaning for scaling control. The way it works is, so this is the cleaning chemical container. We first put alkali. These are caustic based CIP chemicals, and we have a blender. We have the feed tank, which we fill the distilled water with at the neutral pH at a low conductivity, and then we create a homogeneous mix of solution for the pH between 11 to 12, and then we let that water go into this RO, recirculate the same. So the one flow would be, it comes to this RO, both permeate and reject goes back to the same tank, and when you see the pH of permeate and reject goes lower than the 11 or 12 in the feed, it means the chemicals are working with the scalants here. So if the pH eventually, with these low pH diluting the feed, you add more caustic based CIP to keep the chemicals at the right pH 11 to 12. So first you recirculate for about 30 minutes, and then you stop the system, let the chemicals soak within the RO, and then you once you see the permeate pH is the same as the feed pH, it means you have completed your alkali cleaning. And then you open these control valves, let that water out. You fill that with the second round of distilled water. This time is acidic cleaning for scaling control. So you let HCl based CAP chemical or acidic chemical here. You maintain a pH of between 2 to 3. Do the same process of recirculation for 30 to 45 minutes, soaking. And then once you see the feed pH and the permeate and the reject pH being the same, you open these control valve, let it go out. And then you do a final rinsing with the deionized water. You check the feed conductivity and the permeate and the reject the permeate conductivity. If it's per your design, it means your CIP is done. To summarize this cleaning program, so the UF has something called chemical enhanced backwash. This is done more frequent, and this is a preventive measure where the process is you air score, you chemical backwash for a few minutes, and then you soak, and then you clean it. So this is done more frequently than a CIP cycle, which is typically for a 3 to 6 months duration, whereas these are done a couple of days to a week, CEB. And then the ROCAP is what I just explained. So these are acid alkali based chemicals for controlling of scaling and fouling. So one success story for an excellent chemical program by Gradiant is the Savaco desalination, one of the largest desalination players in Saudi Arabia based in Jeddah. So they had a chemical. So what it does is they take borewell water, and then for this desalination, the RO recovery was about 45%, and that RO reject, because of its high TDS, they have to they used our CFRO technology, further concentrated it. Because the operation is handling high TDS, they observed severe fouling and scaling issue, and the pre-treatment was not done properly. So they had to handle high organics, metals, salts, and eventual pressure drop. So unlike usual three-step approach of a CIP, Gradient has been with them with the site, understanding the core issue in the membrane. We proposed a five-step process. We start with the biocide cleaning, then we do alkaline, then we did acid, then we did silica, and then we finished off with biocide. So we took an unconventional approach, although if you look at the overall cost of normal CIP versus ours, were equivalent, although we were five-step approach, because our dosages were low and our time of CIP was much lesser than a conventional CIP cycle. So they could bring back the system to life, although they were originally thinking of replacing the membranes. So till date, the membrane is working fine for over 3 years, zero unplanned downtime because of the right CAP program that we have benchmarked for them. And of course, 99.8% system availability. So to summarize our discussion, we talked about three key challenges being scaling, fouling, and membrane degradation. And of course, customers' objective is to have higher recovery, optimize their chemical program, and membrane longevity, so their operational cost is lower. So the solution is the right chemistries, along with the digital solution to optimize the performance. With these specialty chemical offerings, we can definitely meet these drivers of the customer. So the gradient grade innovation, what are the cure differentiators? So one, because gradient is very strong with brine concentration side, we do high salinity, 25% concentration using membrane treatment. So we have antiscalants in the chemical program tailored for the high TDS application range, unlike the conventional players in the market. Second is we are in the R&D of developing the green antiscalant commercialization to be environmental friendly and also promote R&D towards sustainable future. The third, these are not just products we take from off shelf and sell. We tailor a solution like we saw for the Sabaco. We tailor a solution which has few ingredients as these products that meets or tackles the specific operational challenge. And the fourth, these are high performance chemicals which are fast acting. It just needs lesser time than the conventional chemicals. So eventually minimize the chemical usage. So leaving us with four key takeaways from this webinar. First, Gradiant being a global company who has solutions across 90 countries, we have five chemical manufacturing centers, one in Abu Dhabi and in Saudi Arabia for the Gulf market. The third is in Malaysia to cater to the Southeast Asian APAC market. Italy, we have for the Europe market services. And of course, in India, we have for the Indian market. So the if you travel with me by now, so the key takeaways are obvious. One, we don't sell products as products. We tailor a solution that a customer needs to meet their drivers of high performance, asset protection, lower operational cost, high ROI. So we tailor the right solution for the right drivers, supported by the comprehensive product range of Cure with over 400 specialty formulations. We can very well tailor a solution for our customers. And of course, gradient grade innovation is driving the next gen solutions, creating the paradigm shift towards a sustainable future. So, with that, I conclude and thank you for patiently hearing. Happy to take up questions. Over to you, Keith.
Okay, all right. Well, thanks, Anish. Very informative session, as always. I just want to make sure that folks know to enter their questions in the chat box. Should be in the upper right-hand corner. That way we can look to answer as many as we can. Although we don't have a lot of time today, we'll try to make the most of the next few minutes. So I did see a couple that have been coming through here. So let me go ahead. First question, how does oxidation impact membrane integrity?
So oxidation creates a irreversible damage to the membrane with three mechanisms that I explained. First, it changes the polymer integrity of it. So the first, it changes the polymer surface by breaking the molecular bonds within a polymer. So this is a little technical, but in short, it changes the polymer structure or the membrane structure, and then so when this happens, the function of that polyamide doesn't work. It is designed for selective chemical retention and allowing solvents to pass through. It loses its selectivity effect by allowing all the solvents along with salts to pass through. And oxidation basically increases the pore size of a membrane, and then it doesn't filter as effectively as it used to be. So three key effects, one being surface damage, it loses its selectivity, and third one, it increased permeability, which is three irreversible damage to a membrane.
Okay, great, thanks. Are there, next one, are there any pre-treatment chemistries to protect membranes from this oxidative damage?
So we have dechlorination agent category of chemicals. So what dechlorination does, it basically neutralizes these free chlorines present in the water by basically reducing these chlorine into a harmless chloride ion, which are not oxidizing agents. So these chemicals we offer change these chlorine to become chloride ions. And we let that in the water and that don't damage the water. So we addresses the root cause of an oxidizing agent to become a harmless substance in the water.
Okay, all right, great, thank you. Um, Let me see here. Is there a mild biocide that can kill bacteria but not alter the membrane properties in a negative way?
Absolutely. So, with understanding the water quality that's getting into the membrane, we break down the list of bacteria and we have specific biocides at a diluted biocide version tailored for specific bacteria that can be addressed without damaging the membrane. And we use the right dosage, ppm, so that the membrane integrity is untouched while specifically addressing the bacteria kill.
Okay, great. Might have time for one or two more. How often do you schedule ROCIP? Is there any difference between that and, say, UF? And is there a frequency or recommended frequency for UF, chemically enhanced backwash?
So the frequency of a CIP program is varies for different industries for different water conditions. But on a typical scale, the ROCIP can be any time between a 3 month to a 5 month run rate because these are very critical systems that we don't want to damage. And we have these leading indicators. Today, the sensor technology is so powerful. We can have those leading indicators of a change in pressure drop, flow difference, the water quality. So it doesn't have to be a standard schedule. It can be a predictive machine learning algorithm. So that's what I refer to as smart ops. In all our current offerings to the market, we intend to go with smart ops to kickstart the cleaning program as and when required and not unnecessarily with a conventional scheduled maintenance approach. But on a typical scale, it's 3 to 6 months for a ROCIP and a 2 to 3 months for a UFCIP and a couple of weeks for a UFCEB, chemical enhanced backwash.
Okay, great. Well, it looks like we're at time. So apologies to those who had some questions out there. We do have these, so we will aspire to answer these perhaps as a follow-up after today's webinar. If you could go to the next slide, please. All right, so that's the conclusion for today. As I mentioned, we will be following up with some answers to the questions that maybe we did not have a time to go through today. We'll also be following up with a survey to make sure that we understand, how we did today and continuously improve our content. As you can see on the screen here, you've got both Anish and my contact information, as well as a couple of our colleagues on the Global Chemicals team. The at gradient.com are our email addresses, or if you want to connect with Gradient, you can scan the QR code on the screen there. We certainly appreciate your time today, and we look forward to having you in future webinars. So thanks again for attending, and have a great rest of your day. Thanks.
Thank you all. Bye bye.